We've been doing some calculations involving molarity with stoichiometry, and this video is going to focus on one particular variety of calculations that we do involving molarity and stoichiometry. In class, I demonstrated how we use molarity with stoichiometry to calculate grams of a product, and that's basically what gravimetric analysis is about. Gravimetric analysis is called that. You might notice the word gravimetric sounds a bit like gravity. And gravity is how we calculate weight. And then metric, that sort of sounds like measurements, right? And so that's exactly what we're doing. We're predicting, or we're using the mass of a product in a reaction to tell us something about the reactants. So let's look at a sample reaction. Let's look at lead nitrate reacting with potassium sulfate. And before we go any further, take a second here, pause the video, and look up the solubility of the lead nitrate and the potassium sulfate. Or if you're already familiar with those solubilities, then just go ahead and write the phases in and predict the products. All right, hopefully you did that, and you remembered that nitrates are always soluble, and that potassium compounds are also always soluble. So these two reactions are happening in solution, and sulfates are usually soluble, but not with lead. So this is making lead sulfate as a precipitate, and then it's making some soluble potassium nitrate. Another good practice for you right now to emphasize some of the skills we've been working on would be to pause the video and write out the total ionic and the net ionic equations for this particular precipitation reaction. I'm not going to do that right now, but if you want to check your work, you can talk to me about it outside of class. So let's take a scenario where we're going to do gravimetric analysis. A situation might be something like this. We have 25 milliliters of some lead nitrate, and we have an unknown molarity. Then we've got a solution of potassium sulfate, and we add a bunch of potassium sulfate until we stop making lead sulfate precipitate. So sometimes that can be hard to tell, but let's just imagine that we manage it. So we add an excess of the potassium sulfate. So that means this is not a limiting reagent problem. We have added excess, and we are trying to figure out information about the lead nitrate. So we collect our lead sulfate, we filter our solution, we collect up that lead sulfate, we dry it, and we weigh it. And let's say that we collect a certain mass of this lead sulfate. So what if we get something like 4.962 grams of lead sulfate that we collect? The question that we are going to try and answer here is, what is the molarity of the lead nitrate? So pause for a second and think about if you already have an idea about how to solve this problem. I'm going to recommend that when you look at a problem like this, just like we have been doing, I know this is probably getting repetitive, but my hope is that this will become so ingrained for you that you just automatically use this kind of a flow to solve your problems. The reason why I'm really focusing on this is that these calculations can all seem really unrelated to each other. But I want you to start to see that this is one sort of like a spiderweb map that we can get from one place to another as long as we use the right tools. So we've done quite a bit of calculation going from grams to moles to grams. And we use our balanced equation every single time. But we've added this new track that has molarities as the way that we're getting from one thing to the next. So the process is what I really want you to focus on here, okay? When you solve these problems, this is your process. The first step is to identify our A and our B chemicals, okay? So look at the chemicals and this question: what is the molarity of the lead nitrate? What kind of information do we have? Hopefully you were able to identify that the lead sulfate is our A because we've collected a certain mass. And so this is where we are for starting for this problem. And this is always where we're going to start with gravimetric problems. And if we're looking at B, that's this question, right? The lead nitrate, oops, I left out the 2. This is our B. This is a thing we want to go toward. But where over here on the B side are we going to? What is the molarity? So unlike all the rest of the calculations we've done, we're actually going over here to this side. This is where we are going to end. So let's map out what has to happen. Our first step is easy. We've got grams. We're always going to go to moles. Oh, I need to write my second step in the process, which was to identify the start and the end. So we're always going to take grams and convert it to moles. This should be very familiar by now. And we're always going to use a stoichiometric relationship as well. So that's going to be our balanced equation. And that's going to be, here's our step 1. Maybe I better label. I'm running out of symbols to use, so we'll worry about that later. So we need to go grams to moles, moles to moles, and then look, we have moles, we have volume. At the very end, we're going to calculate the molarity by setting up moles of B divided by the volume of B, which we already have. All right, so this is our strategy. So I want you to pause the video now and try setting up this entire flow and calculating the answer. You're going to calculate grams of lead sulfate and convert that into moles of lead sulfate. Use the balanced equation to get moles of lead nitrate, and then divide by the volume to get the molarity. So pause the video and go do that. All right, welcome back. So hopefully this was a good calculation for you, and you started with 4.962 grams of lead sulfate. Now our gram to mole, we need the molecular weight of the lead sulfate. So I calculated that, and hopefully I did that right. I got 303.26 grams of lead sulfate. And we know that our molecular weight says 303.26 grams is how many grams of lead sulfate are in 1 mole. So I've set up my units to cancel out the lead sulfate, and that leaves me with moles of lead sulfate, which means I'm right here. So my next step is to use the balanced equation to get between moles of sulfate and moles of lead sulfate. So if I look at the balanced equation, I can see that these are 1 to 1. So 1 mole of lead sulfate goes on the bottom so that I can cancel out those units, and 1 mole of lead nitrate goes on the top. So when I check back in with my calculation, I can see I actually want the moles. So I'm going to stop right here and go through this calculation. Okay, so when we do this calculation, I get 0.01636 moles of lead nitrate. So now let's check back with the question. What was the question in the problem? Our question said, what is the molarity of the lead nitrate? Have we done that yet? No, but we did calculate the moles, and we know that molarity is just moles over volume, so we're almost there. Okay, so we're going to take moles, 0.01636 moles of lead nitrate, and we're going to divide it by the volume. It has to be in liters, so let's check back. What was our volume? Here it is, 25 milliliters. So 25 milliliters divided by 1,000 per liter is equal to 0.02500. Please don't lose those 2 zeros at the end. Those are significant. This means that you very carefully measured the volume, probably using a volumetric pipette, and you put a lot of effort into that, so don't lose those guys. So we're going to divide by 0.02500 liters of lead nitrate solution. And so if we divide that out, I get 0.6545 molar lead nitrate. Hopefully this is the problem or the answer that you got as well. So if you didn't, then just check back at any of these steps and figure out what happened here. But let's go ahead and try this again. Try another practice problem. We'll use the same system just so we don't have to recalculate any of our molecular weight numbers. So let's go ahead and I'll set this second one up. So another example problem using the same system might be, we collect 18.41 grams of lead sulfate when we react 35 milliliters of lead nitrate with excess potassium sulfate. What was the molarity of the lead sulfate solution? Oops, excuse me, I mean lead nitrate. All right, this time I want you to pause the video for sure, and I want you to set up your flow, do the things we just did, all right? So here's our balanced chemical equation. Here's our plot. We're actually taking the same path we did before. So make sure you identify A and B, identify the start and the end, and then go through this calculation. All right. Now that you have done that, let's check your work. When I take 18.41 grams of lead sulfate. My setup is exactly the same as it was before. So when I divide that by 303.26 grams of lead sulfate per 1 mole of lead sulfate, and I convert that into moles of lead nitrate, then I got 0.06071 moles of lead nitrate. And just like before, we calculate the molarity of the lead nitrate, and I'm using shorthand notation for molarity of lead nitrate here. I mentioned this in class as well, that when I use these square brackets, this is shorthand for molarity of whatever is inside the square brackets. And you'll see this a lot, so I want to make sure you get comfortable with this notation. So we have 0.06071 moles of lead nitrate, and we're dividing it by 0.03500 liters. Don't lose those zeros, so you can keep 4 significant digits. And I got that the molarity was 1.734 of the lead nitrate. Hopefully you got that too, and that these calculations are causing you no difficulty at all. So one of the things that I want you to take away from the strategies that I'm using here is that I want you to focus on the process. I don't want you to try memorizing equations and stuff like that, because memorizing equations becomes super overwhelming. But if you can memorize anything, then I want you to memorize our flow chart, okay? That you will be able to reproduce this flow and use the flow, and we're adding to the flow all the time. I mean, not indefinitely, but you can see in that worksheet 4 the map that we are eventually going to and how we have a lot of different pieces that are connected to them. So if you can follow this process of identify your A and B, and then identify your start and your end, and if you can get between each of these individual steps, you are going to be able to solve every single problem that we do involving stoichiometry. And it will just be a matter of finding your place on the map, and then finding out where your destination is on the map, and going in between those two. So the other thing that I want you to really make sure that you are doing during these videos is that when I ask you to pause the video and do the problems before I show you, it's really critical that you do those. You need to have the practice of going through the process of it, of trying it out. This will create what's like, muscle memory inside your head. I know that your brain doesn't actually have muscles in it, but it will create neurological pathways for you so that when you see a problem that looks like the kind of problem that we've been doing, your brain will just click into gear and it will follow through the process, and you will be successful at solving these problems. So hopefully this has been a relatively short motivational speech, and you are now persuaded to follow these processes. All right, good luck, and you'll see some of these problems on our next worksheet.